I can talk already about the first slide because the first slide is actually summarized quite nicely by the two pictures there and there. So I can't really claim that those are my own pictures. I may have borrowed them from a website somewhere. But what I'm going to talk to you today about is how we can characterize catalysts, how we can characterize structures, and the role of synchrotron and neutron sources in this. In particular, I'm going to talk about two different case studies. One is an EXAF study, which I did during my time here with Andy Beale, looking at palladium on indium. And we're going to be talking about CO2 utilization. And the other study is going to be using small angle neutron spectrum scattering on hierarchical materials to try and explain some catalytic behavior. CO2 utilization, we've already heard a little bit about this over the course of the conference, and I'm sure we're all aware why we need to utilize CO2. Apart from the moral factor, there's going to be a lot of very cheap CO2 soon, so it's going to be a very nice cheap reagent that we can easily get hold of and do things with. And despite this, as one of the previous speakers talked about, the amount of CO2 is growing year on year on year. A little bit of a dip for the pandemic, but it's back to increasing all the time now. And there's a wide range of things we can form CO2 from. So we talked about methanol, urea. Some people are even bonkers enough to build polymers out of it, Charlotte. But there's a wide range of things we can do with it. With methanol, it has a wide range of uses. It's used almost universally. Formaldehyde, chloromethane. But we also need to put things into context. And in order to get to net zero, we need to capture an additional 10 gigatons of CO2 every year until 2050 and then carry on. If we produced all the methanol in the world from CO2, this would take 110 megatons. That's about, back of the envelope, 1.5% of the amount of CO2. And methanol is quite a bulk product as well. So as you can see, we need to capture a lot of CO2. And it's, I'm probably not doing a very good job hiding the fact that my research area is also in CO2 capture now. So read into that what you will. For CO2 utilization, one of the speakers already mentioned that the copper on zinc oxide on alumina is the commercial catalyst. Normally, this is done with syngas, a mixture of CO2, CO, and hydrogen. However, we want to try and do this just CO2 and hydrogen. But the problem with the commercial CZA catalyst is one of two things: a very high CO selectivity, which we don't want, and also a very quick deactivation rate. So this is an issue. This has caused people to look for alternative systems, and one of them was indium oxide. Indium oxide was particularly of interest because it's a commercial catalyst for the reverse process. If it can do the reverse process, maybe it can do the forward process as well. So people have tested it in the literature. This orange line corresponds to the indium oxide. The blue line that you can probably see here is a CZA catalyst. And the indium oxide had an incredibly high selectivity for methanol. Unlike the CZA, it had slightly lower activity, but this is a good start. Selectivity is always better to start with than conversion. The reason indium oxide is such a promising catalyst for this is that indium oxide can have oxygen vacancies on the surface. So you can see here, we've got an oxygen vacancy, or in the V4 position, we can have an oxygen vacancy. CO2 can bind to these oxygen vacancies, and it's more easily activated than CO2 on its own. However, we have to be careful. Some vacancies are good, too many are bad. If you have too many vacancies, the indium just starts to reduce completely, and then it deactivates. So we've got a system which can potentially activate CO2. However, to be a good CO2 utilization catalyst, we also need something that can activate the hydrogen as well. And so, unsurprisingly, people decide to put palladium on it, a very common hydrogen activation catalyst. There's quite a fierce debate in the literature at the moment about whether having a palladium-indium alloy, a single phase containing both, actually helps or hinders the reaction. Some people are very pro the fact it helps, some people are very anti it and say it hinders the reaction. But one thing for sure that everyone agrees on is that having the two together, whether it's in a single phase or just two constituent parts, definitely improves the activity. And while palladium-indium is a fantastic system, sadly, they're both quite expensive. So one of our collaborators at the University of Bologna prepared some samples where they diluted the amount of palladium and alumina by putting it, palladium and indium by putting it on alumina. And what we can see on the far left here is the STY, the space-time yield of methanol here for the pure palladium on indium sample. And by having just 1% palladium and only 12 weight percent indium, we can see that actually this activity matches pretty well, even though we've got about 8% of the 8%, 12% of the metal in our solution. So this is a much more efficient, effective catalyst. And we chose this to look at why the palladium and the indium actually complement each other and why they improve the reactivity. To do this, we went to diamond light source to B18 to do an operando X-ray adsorption spectroscopy measurement. This had two steps. The first step was we wanted to reduce our catalyst. This is a common first step when doing reductions. And we did this at 5 degrees C up to 300 degrees C in a reducing atmosphere. This was the easy bit. The hard bit, which involved lots of glue and swearing and breaking capillaries, was the second step. This was the actual reaction where we flew in hydrogen and CO2 and 20 bar of pressure. To do this reaction, we gently ramped up the temperature. We took a scan, ramped it up, took a scan, ramped it up, took a scan. And I'm not going to go into too much detail about the background of XAFs, but just to show you that what we have on the x-axis here is energy, and what we have on the y-axis is intensity. And what we saw as we went from the black 30 degrees C to the red 300 degrees C is a shift in this signal, and we can see the features changing quite noticeably here. Shifting from the right to the left means a reduction in the metal. So we can see, shockingly, as we exposed palladium to hydrogen in temperature, we reduced it. I know you're all surprised. What we also saw is a decrease in this signal here, which is palladium oxide, and we saw a growth in this signal here, which is our palladium metal. What we did not see was any features that we could ascribe to palladium and indium. And what we noticed is the main change happened at about 165 degrees C. We then went to look at the indium site as well. And as you can see, there's not really a shift here. We can't really see any change in the oxidation state. What we can see is a decrease in these features here, but this is just a decrease. It's not a change. We're not seeing new features evolving. This is just a system decreasing slightly. We looked at the R space here. This feature is due to the indium oxygen bond, and we can see that this decreased. There's two reasons for it decreasing. One is that as you increase the temperature, you get more disorder, more uncertainty, so your signals naturally come down. The other reason that we saw is that this could be due to the oxygen vacancies forming. Crucially, we didn't see any indium or indium-palladium features. So far, we're quite confident we're not really seeing an alloy here. We've got our palladium and we've got our indium. What we were able to do, because we have a reference for what metallic palladium looks like, we have a reference for what oxidic palladium looks like, we're able to calculate roughly what percentage of our sample is oxidic and what's metallic. And we were able to plot this as a function of the temperature. In red, we can see that as we reduce it, we are getting to about 80–90% of metallic palladium. And then during the reaction, this stayed pretty constant. And this actually tells us that the reduced state before having to do the complex operando catalysis is actually a very good descriptor for the catalyst. If we then looked at a similar system, the indium system as well, we saw during the reduction that the number of indium oxygen bonds decreased. And again, this stayed very constant during the reaction. So once again, in this situation, the reduced state was a very, very good descriptor for the actual reactive system. We then looked at some infrared measurements under operando conditions. What we could see if we focused just on palladium was that the formate signal began to grow as we go from blue to purple, but then it came back down again. The reason we had for this is that the palladium is very good at activating hydrogen. And as you got to higher temperatures, it was activating hydrogen so fast that the formate and the CO2 activation just wasn't able to keep up at all. So this isn't an optimal system at all. So as we concluded, formate production cannot keep up with hydrogen production here. We then looked at the indium on its own, and we saw the reverse trend. We saw the formate happily growing and growing and growing and growing, and it just kept growing. So this again tells us that here, indium, fantastic at activating the CO2, however, very slow at activating the hydrogen. So we then looked at the combination here, the palladium-indium. We saw the formate was beginning to grow up to about 225 degrees C, and then it started slowing down. So we've actually got a very nice catalyst here where we can see that the indium is able to activate CO2, and then the hydrogen kicks in as well, and we can form methanol very nicely. So here, the combination of sites was very effective, and it was very important for this reaction. And this is the mechanism we came up with, that, unsurprisingly, the palladium was able to activate the hydrogen in close contact to the indium. We think this is quite important, that whilst we didn't form a single palladium-indium phase, we did form a interface, because otherwise, how is this spillover happening? The palladium is able to supply the activated hydrogen, which then takes the formate, reacts with the formate on the indium, and this is our proposed pathway for this. And this was our conclusion from the first half. Indium oxide's very selective for methanol formation. Palladium improved the activity. The operando X shows that the reduced number is a very good descriptor for catalytic activity. We saw absolutely no signs of alloying, despite desperately looking for them, and that the palladium and indium provided very complementary roles in the reaction, and this is possibly due to subtle interactions. So this is the end of the first case study. I'm aware I've been talking for longer than the average attention span of the undergrads. So if everyone just wants to have a quick mental refresh, we'll start again and go for the next round. So I'm going to talk about porous catalysts. This is some work I did at Southampton. I was at Southampton for quite a long time working on porous catalysts. So at this point, I think I'm legally bound to talk about it in every single talk I give. So the main thing we're talking about is microporous materials. We've heard talks about zeolites and sapos already in this conference. And this particular one I'm showing you here is Sapo 5. This has a pore diameter of about 7.3 angstroms. Microporous materials are absolutely fantastic for catalysis. They're great in the way that they give you so much control over the reaction you're doing. You can control what reagents can fit into the pores and therefore reach the active sites in the middle. You can control what transition states form by forcing the reaction to happen inside this confined environment. You can also force alternative products to form that wouldn't normally happen. There's papers where people have taken cyclohexane and turned it to adipic acid, which is certainly not in the undergraduate textbooks. However, there are also issues with them. And one issue is that because it has a very small pore size, you can't use bulkier substrates. There's a lot of interest in using bio-based materials, and some of these just won't fit in. Polymer deactivation, some of these might not be able to fit into the pores either. And also, they can deactivate. If you start forming very bulky materials, very bulky aromatics, these can quite happily sit in the pores and block them off. So now your catalyst has fewer accessible active sites. It's not as effective. So one of the things that's been quite fashionable recently is something called making hierarchical materials. And these have two different types of pores. We can see here, I've just zoomed out. This is my Sapo 5 pore that I was talking about before, 7.3 angstroms. This is a micropore still. And now we also have, and now we have a mesopore as well. And these ones that we're looking at are typically in the nanometer range. People might be familiar with things like porous silicas, SBA 15, MCM 41. These are all very good mesoporous systems. And there are two main approaches that I've looked at for making these hierarchical materials. One is something called soft templating. This is where you add a surfactant in a similar way you would form a normal microporous system. You'd have an organic template for the system to form around. You calcine it to remove it. This is a very similar system. You can see there's a very long, bulky organic group here, but also importantly, there's a silica head group. And this we'll come on to later as to why it's important. I'm not claiming to have pioneered this technology, by the way. This was done in 2006. I am simply jumping on a bandwagon a little bit too late. Another way is hard templating. Some of the previous speakers have talked about carbon systems. This is a more straightforward way in the fact that you already have some very nice carbon systems with very defined pore sizes, very defined shapes, and you can put those into your material for things to form around. Whereas when you're doing a soft templating approach, you're hoping that the micelles come together and form the right shapes. And again, very late on the bandwagon. This was originally done in 1999. However, it's still a very interesting and fascinating area. The chemical reaction we were looking at is butane isomerization. This is a very important reaction because the amount of isobutane we get from natural gas and from refining oil is not enough. So we have to then isomerize some of the leftover N-butane to get isobutane. And this is a vital petrochemical intermediate. It's important for forming isobutane, alkylates, oxidants like TBHP, and it requires very strong acid sites. As you can tell, this work wasn't sponsored by a small sustainable SME. It's very much petrochemical here, which still is very useful and will still be useful for the next 50 years, I'm afraid. So what we did is we wanted to add our mesoporogen. This is DMOD. This is the molecule I was showing you earlier with the long organic group and the silicon head group. We took our synthesis of a microporous system and we just kept adding more and more mesoporogen into it. The idea we had is we wanted to see, can we build up a model of our microporous system, how it works? Can we see how the hierarchical system compares to the microporous system, and then try and tell how accessible these pores are? And I'm very proud to say that the hierarchical system did not perform as well as the original microporous system. So we had a rather distressed undergrad in the lab that needed some consoling for a few weeks after these results. But our microporous system, we got about 12, 15% conversion here. The hierarchical systems all had worse conversion, slightly better selectivity, but that's to be expected if the conversion is slightly lower. So we were slightly confused by this. We'd been promised by everyone doing porous materials that hierarchical materials were the way forward. So why hadn't our reaction worked? And we wanted to find out why this is. So we went on to look at the porosity first of all. These are nitrogen absorption isotherms. The red line in all of these is the microporous system. And you can see this is a nice flat line here and with a jump at the low pressures. And this is telling us this is a very nice microporous material. It's exactly what we expected to see. When we add our mesoporogen, we have still retain our nice jump up at low pressure, which suggests there's still some microporous material in there. And then we see this sort of hysteresis here. We see an increase at higher pressures, and we see this gap here where the adsorption and desorption legs of the isotherm don't match up. What we're then able to do is analyze the pore widths of these different materials. Here we can see the red microporous material had very little features. There wasn't really anything there at all. And this is exactly what we'd hoped for because we wanted it to be a microporous system. What we saw when we added the DMOD, the mesoporogen, is that we not only made mesopores, but we can see that this peak, which corresponds to the average pore width, starts decreasing the more of the mesoporogen we added. And this is something that's quite confusing. We weren't sure why this happened. So we decided to look into a little bit more detail about the porosity. And there's a great number of techniques we can use to look at porosity. Santosh told us about QUENS yesterday. Mercury porosimetry is also a possibility. Positron annihilation lifetime spectroscopy, and also small angle scattering as well. We went for small angle scattering because we knew how to do it, and we had a source locally, and also QUENS at ISIS has been down for a number of years, so that wasn't really an option for us, sadly. I'm going to give you a quick overview of how small angle scattering works in very cartoonish ways, but it is more complex than this. The idea between small angle scattering is you have phases, and each phase has what's called a scattering length density. I'm showing here we have a two-phase system. We have our black square and our white circle. The intensity of the small angle scattering signal varies with the square of the difference between these two phases. So as you can see, this would give us a very strong signal, very big difference. This is going to give us a weaker signal still, very, very weak signal. And that's how small angle scattering, in a nutshell, works. The useful thing about small angle scattering is that it's actually quite intuitive as well. So this is actually a small angle scattering data set. And you can see on the x-axis here, we've got Q, which is units of inverse angstroms. And on Y, we have intensity. These are both on log scales because they span quite a wide range of data points. At low Q, we have what we call large features. This is telling us about the particles, it's telling us about the particle size and the particle shape. And then as you go to a higher Q, you start getting smaller features, things that are due to the nanoscale. They could be due to our micropores. They could be due to defects in the way things are arranged. And we also get Bragg peaks because, of course, we get Bragg peaks. Everywhere is Bragg peaks. Now, there are two different ways of doing small angle scattering. There are SACs, which is with X-rays, and SANS, which is with neutrons. Small angle X-ray scattering is faster, typically, has higher resolution, more intensity. And to be quite honest, I probably should have chosen that over SANS, but I like neutrons far too much, so I went for SANS anyway. The advantage of SANS over SACs, though, is the cross sections. I think we're all familiar with the idea that with X-rays, the heavier the element gets, the more the X-ray sees it, the more sensitive it is to the X-rays. With neutrons, that kind of goes out the window, and you can see this lovely graph here where it looks like my 3-year-old has had a go at writing her own name, to be quite honest. It's gone up and down and everywhere. But the beauty of SANS is something called contrast matching. And water and D2O are basically at the opposite ends of the contrast matching for most materials. Why is this exciting? Well, this is exciting because it means you can mix them together and get basically any contrast you want. So let's say you have a 3-phase system. Let's say you have a pore with around an inorganic support with a polymer in it. You've got 3 phases. Well, this becomes very complicated because now we've got interactions between phase 1, phase 2, and phase 3. So we've got 3 different interactions. What you can use contrast matching for is to simplify this process. What I've got here is a black square with gray circles and my white empty pore. I can tune what I put in my pore to exactly match those contrasts. So for example, I could make a solution of H2O and D2O that perfectly matches the support. And now all I have to do is worry about signals from my gray circles interacting with the black spore. Got a 2-phase system. And then I can do the trick the other way as well. So I can make my contrast so that I match the gray circles. It's a very elegant way of simplifying things, and it's very, very useful. And the people at the ISIS deuteration lab want me to point out they are now fully active. And so if people want to do this kind of thing, it's perfect for deuteration lab stuff. I'm going to give you an idea now about how I fit this model. This is the data from the microporous system that I showed you a little while ago. The thick black line is the actual data. The skinny pink line is the fit. And what I needed to fit this data is I started off with my flat background. This is my straight blue line here. I then added 2 Gaussian peaks. The reason I had to do this is because my material is crystalline and it had 2 great big Bragg peaks exactly where I wanted to look for my nanoscale. So I had to fit those as well. I then had a power law, which reflects the roughness and the size and the texture of my particles. And then I included this fractal system here, which we believe represents something to do with our micropores. I then wanted to see what the system would look like if I added in these mesopores. And there's a few systems that we can see that are very different. We can see we've got 2 extra lumps here in our 3 mesoporous systems. These all look quite similar, but the area I got really excited about was this area here. This made the 5 days of beam time all worth it, as I'm sure you can agree. The interesting thing here was as we increased the amount of DMOD, amount of mesoporogen, we can see this increase here. And this is what we were very excited about. We started off by using the same model we had for our microporous systems and to apply it to our hierarchical systems. And this is the residual. We've got Q here, and we've got our residual intensity here. You can see the red line, quite happy, nice and small, very low residuals. And you can see these absolutely massive peaks here and here, where this was not a good fit at all. But again, our interesting area, we can see this increase here and here and here, where our mesopores were. So we had to come up with another brand new model for this. We kept a lot of the original model. We kept our flat background. We now had 4 Gaussians. We had to model these humps somehow, kept our power law, kept our fractal. And the important thing that we added that is new is this core shell sphere here. And this very much, you can see the peak here will be influencing this area here exactly, which lines to our mesopores very nicely. And this is our residuals now. You remember we did have some lovely peaks up and down here. This is now a very nice fit for our system. So what does this all mean? Why was I excited about this? Why am I telling you about this? Well, the interpretation was our 2 new Gaussians, we thought these look in a very similar position to Bragg peaks, like you get in MCM 41, SBA 50, excuse me, just general mesoporous silicas. And these actually added up that the D values were basically half of each other. So this gave us very strong evidence that this could be a 0,1 peak and a 0,2 peak as well, or a 1,1 peak. This suggests that while the mesopores might not be completely ordered, there could be some evidence for long-range mesopore order. What we were able to do with our core shell model is we managed to fit the width of the core, and this trend matched very nicely with our BET. We can see that as we increase the amount of mesoporogen, 0.1 to 0.2 to 0.3, the pore width went down, which is the same that we saw with the BET. The values were not perfectly adding up. To be honest, getting within a factor of 2 from a generic BET pore width fitting and a SANS model is actually quite good. They showed the same trend though, which we're very happy about. The other thing we noticed is that we could fit the scattering length density of this shell. And we were hoping for something like a porous system, like, with like silicon. However, the value for the scattering length density of the shell that we got was almost exactly the same as dense silica. I mentioned that our surfactant had a silicon head group on it. What it had decided to do, instead of forming a nice accessible pore, was basically coat the inside of our mesopores with very dense silica. So the reason our catalysis hadn't improved at all is because the mesopores were essentially almost inaccessible and useless for us, and blocking any access to the internal active sites. So on reflection, I probably should have called this SANS reflection because that sounds like I've invented a new neutron technique, but we were able to modify the mesoporous layer. We confirmed that our mesopores were actually coated by an impermeable silicon layer. We were able to reproduce the trends from BET and also PALS, but I didn't want to show that work because you can only show so many characterization techniques. And one of the things I wanted to highlight is that this really shows the need for care with hierarchical systems. When we used our soft templating approach, we got worse catalytic activity. In the paper we've just submitted about hard templating, however, we got better catalytic activity. So not all pores are created equal on this side, in this case. Hopefully I've shown you that we can expand SANS to other systems. Porous systems are beautiful for SANS, and it has got a place aside from SACs. I was being very flippant earlier, but thankfully my beamline scientists aren't here for SANS. And it is proven to probe porosity very nicely. I'm going to finish up the talk now by just thanking a few people. As I said, this work was done during my time at Southampton and also at UCL. Andy Beale, who's in the audience, put up with me for a few months. I want to thank the co-authors on that paper, Emma Campbell, Sophia, beamline scientist Steve Parry, our collaborators in Bologna, and our other colleagues who are at the Cat Hub. And I also need to thank my long-term boss at Southampton and the team from Southampton, particularly Marina, who's in the audience, and the beamline scientist who had to keep explaining to me why we couldn't do exactly what I wanted to do, and these things about health and safety. I'd like to thank the money and the funders as well. And finally, I'd like to thank you for your attention, and I look forward to answering your questions. Thank you.
Okay, we've got plenty of time for questions. So,
Thanks for a wonderful talk. First, I just want to clarify something. Did I get it correct that you concluded that the microporosity that provides transport to the mesopores was blocked?
The other way around. So the idea behind a hierarchical system is that the mesopores are there to help funnel the reagents into the micropores, which contain the active sites. In our case, a lot of the mesopore was blocked by this impermeable layer. So it almost created a trap for our reagents. So once the reagents went in, they couldn't access the active sites, which is why our catalytic data was worse.
And but the scattering data showed that you did or did not have those micropores.
We still have the micropores.
Right.
So
You can't access them.
we can access the majority of them. It's just the problem is that the mesopores are sort of creating an unwanted diversion. So instead of our reagents just being able to go in and access the micropores as we want, maybe they take a right turn and end up in a mesopore that's a dead end, essentially.
And then just the last quick one is, have you thought about NMR relaxometry as a complementary tool? I think it could have something nice to offer.
I think it would be a fantastic technique. Yeah, I think I already am told I have a problem with collecting characterization techniques, but I'm always happy to add one more. So it's definitely something I'd be interested in.
can I ask? So you said in the palladium indium system there was no alloy.
Yeah.
I was trying to look up what the palladium indium distance was. What is that compared with the palladium distance?
It's actually very similar,
Okay.
annoyingly.
Okay.
Yeah.
So how?
So the reason we determined it is because we couldn't see anything in the indium at all.
Right.
And we also looked at the temperatures at which the changes started to happen. The palladium change happened quite a little bit earlier than the indium as well. So that's one of the ways we.
Okay. Thank you. Graham.
Mine was a very similar point. I'm surprised you haven't formed any alloy. So I was just wondering, is the temperature at which you're looking at this? If you reduce it at a higher temperature, would you then see the alloy? This is the system we're looking at. So I'm surprised you haven't seen it.
It's very possible. I think one of the reasons that we didn't see the alloy as much as expected is because our material was more metal efficient, shall we say. I'm sure if we had pure palladium on indium, then just naturally you're increasing the concentration of both parties. You'd expect to see more alloying. But because you've got less metal on the system, we think it's less likely that we're forming the alloy.
Well, what loading was your palladium?
The palladium was 1 weight percent and the indium was 12 weight percent.
Yeah. Okay. Yeah, I'll have to think about this as well. But it's a very interesting system.
Oh, very, very.
Very interesting. Thanks.
Thank you.
Can you co-precipitate those two materials?
That's how it was made. Yeah, it was made by co-precipitation. Yeah.
Did you have a question?
Which phase do you think you'd form the alloy in? Because the indium's obviously an oxide.
So you can form sort of palladium indium alloys at the surface. I think that's what we were postulating could form, but that's all really. There's a whole range of different palladium indium alloys. I think there's about 7 different ones that can form. So there's definitely room there for a very systematic study of which alloys you can put on the supports and what does their activity do. But there is a range that can form. Yeah.
Thank you.
Richard?
Mark, the indium oxide, you need the vacancies.
Yeah.
But you don't want to have too many, apparently.
Yes.
So do you know what the optimum concentration is of vacancies?
So I remember reading that I think if you go more than sort of 5 monolayers deep, 5 layers deep of the indium oxide in terms of the vacancies, that's when it starts to fall apart and starts to degrade.
And are these vacancies essentially excentric? So the vacancies with trapped electrons?
I believe so, yeah. I think so. There's been a lot of computational work at which I have to admit I'm not as familiar as I should be, but I think that sounds familiar, yes.
And just a quick comment on the sounds.
Mhm.
Beautiful work.
Thank you. Yeah,
And I think it'd be very widely applicable.
I think so too. Yeah,
Porous materials, the zeolite community should be aware of this.
I agree. It's an area that's previously been dominated by sort of biologists and soft materials, but I think the sands people are starting to come around to it, I think. Thank you.
Question at the back.
That's a really nice talk, thanks, Matt. Just wondering, what do you reckon would happen if you added zinc to the palladium indium system? Do you reckon that would improve its performance?
Well, I'm conscious that Graham is in the room, and I believe he's working on this, so that might be something to ask him later at the coffee. Yes, the more elements you add, you can solve the Schrodinger equation for a hydrogen atom. As soon as you add in more electrons, it becomes unsolvable. So adding in more components, it does increase the catalytic activity, but you've got a lot more interactions to consider, which become more and more complex. More challenging and exciting, but more complex, I think.
Thank you.
Okay, final question, Santosh.
Thank you, Matt. It's very nice talk. My question would be on the reaction mechanism.
Mhm.
From CO2 to methanol,
Mhm.
you have seen that it's through formate,
Yes,
but do you also see some methoxy, and what is their role?
we do see methoxy eventually, yes. So what we saw in our drifts was that forming the formate is relatively straightforward to happen, but then you need to give that formate a kick to get it to go, and that's the slow step of the reaction, is activating that formate. We didn't see a lot of CO in our species, in our reaction, and that's the beauty of the indium oxide. So the vacancies that we were talking about actually stop CO forming, because the fact that indium can give up an oxygen, as CO binds onto it, it can give up that oxygen, form CO2. So yeah.
Okay, final question.
Thank you, very nice talk. The usual soft templates used for the synthesis of microporous materials, they just, make the micelles and other kind of nanodomains. They do not have any alkoxide linkages. In your case, this surfactant itself can do the hydrolysis and condensation, and then doesn't it then complicate the system? And did you try not to use some surfactant which doesn't have the alkoxide groups?
It always complicates the system. Yes, we have tried others. So we've tried sort of phosphine-based systems. The difficulty you have when you're choosing your surfactant is you need it to be distinct from the microporous template, because otherwise, if you add too much of a different surfactant, you can start damaging the microporosity and starting to form other phases. So we've tried a few others. We've not done a sort of thorough screening, but that's a piece of work that's out there to be done, I think.
Thank you.
Thank you.
Okay, I think with that, we should thank Matt for a great talk again.